Hi girls, just want to give you a brief example of energy profile diagrams here. I'm just very quickly going to go through it with you to see if it makes a little bit more sense than it did in my notes. All right. The first place to start is what happens during a chemical reaction. So in a chemical reaction, we have two things. We have reactants that turn into products. And at the end of that, if we have a thermometer in that reaction, we can find that it's either hotter or colder at the end. And a lot of that has to do with the energy and the energy transitions that happen during that reaction. So I want to show you an example of something that we can do to help us understand that. And one of those things is this graph here. We can draw a graph of the energy in a reaction like this. And the way we do that is we draw what's called an energy profile diagram, which is literally a diagram of what happens to the energy in a chemical reaction. So you have to remember there's always some energy at the start of a chemical reaction, because if there was no energy, everything would be absolute zero. There'd be no heat whatsoever, and we wouldn't be alive in the first place. So by virtue of the fact that we're sitting in a room at around 20 degrees, there's energy in that reaction already. So a good example of this is when we turn on our Bunsen burners and we mix the gas in our Bunsen burner with oxygen. Okay, we turn on our Bunsen burner. There's already some energy in there in the room because it's at around 20 degrees, but nothing happens, right? Because what do we have to do? We have to put energy into those reactants to make them work. And that's all to do with collision theory. And we learned about this when we talked about how reactions happen. So what happens is that particles collide with enough energy to form new bonds and new products. And when that happens, reactions happen. So how do we get those particles to collide in our when they come out of the Bunsen burner to make enough energy happen? Well, we have to put energy in, and we do this, in the case of the Bunsen burner, with the form of lighting a match. And we call this the activation energy. And the activation energy is the energy that we have to put into the chemical reaction to make that reaction happen. All right? And that's up here. So that means we have to put energy into those particles to make them react. Now, what we're really doing there is we're breaking the bonds in the molecules in the oxygen and in the methane gas that comes out of the Bunsen burner in order that they can react. Once those bonds are broken, the new bonds will form. And when new bonds form, heat is released. So now heat starts coming out of that reaction and out of those bonds. And overall, what happens is heat is released from our Bunsen burner. So overall, you can see that more energy came out of this reaction than went into it, which we kind of know, don't we? That when we turn on our Bunsen burner and light it, more heat will come out of the Bunsen burner than we had to put in with our match. And this is called an exothermic reaction. Think of an exoskeleton is on the outside, isn't it? So heat comes out. And that's an exothermic energy profile diagram is what that's called. And I'm scribbling one here just to try to explain this, but there's a better one in your notes. Okay, so that's one alternative that can happen in a chemical reaction. I want to show you another one. Let's say we start off with a similar reaction this time, right? And again, when the reaction happens, we put in some energy to get the reaction started. This is our activation energy, right? So we've broken the bonds, we've got the energy going, we've got it started. But this time, when heat is released, enough heat, it never reaches the point where more energy is released than was absorbed or taken in. So instead, we end up here. Can you see the difference? So we started out here, but we actually never reach that point again. We never release enough energy as was absorbed by the reaction during the activation energy step. So in this case, overall, more energy has gone into the reaction than has come out. So the temperature will go down in this case. So overall, what we'll notice in this reaction is that the temperature go down. Here, the temperature went up. So overall, in an exothermic reaction, the temperature goes up. In an endothermic reaction, the temperature goes down. And we did an example of this in school when we looked at one of those packs that you put on your knee, for example, or your ankle if they're a bit swollen, and you crack them open and you mix the two things together and the temperature shoots down. It gets really, really cold. And that's an endothermic energy profile diagram. We've put enough energy in to make it react, and then when the energy is released, it never actually releases as much energy as was absorbed by the system overall. So overall, the temperature goes down. So in an endothermic activation energy diagram, the temperature goes down. In an exothermic one, temperature goes up. These diagrams are a bit sloppy, guys, because I'm just scribbling them here for you to try to explain it a bit better. There's better ones in your notes, but hopefully this helps you to understand it a little bit more. And thanks again to Laura for asking me that question. Okay, hope that helps.